So the goal of this first lesson on sequences is to learn the notation and terminology used in this topic. So a sequence is a set of terms written in some order, and we can study sequences when the terms are numeric and there's a pattern in their order. Tn, that's T subscript n, denotes the nth term of a sequence, and a sequence with a finite number of terms is called a finite sequence, and a sequence with an infinite number of terms is called an infinite sequence. So two quick examples, 3, 5, 2, 11, 4, 12, 1, 7 is a finite sequence of 8 terms. You'll notice there's 8 numbers there. There's no apparent pattern in the order of these numbers. And term 1, T subscript 1, is equal to 3. And the last term there, T8, the 8th term, is equal to 7. In the second example, 1, 8, 27, 64, 125, comma, dot, 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 this is an infinite sequence, which is denoted by that comma, dot, 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 to show that it keeps going. And here the terms do follow a noticeable pattern. When the terms follow a pattern, we can usually write a formula for the nth term of the sequence. And in this case, hopefully you can see that Tn is equal to n cubed. So term 1 is equal to 1 cubed. Term 2 is equal to 2 cubed. Term 3 is equal to 3 cubed, etc. So let's now have a look at a number of examples where we apply this notation and terminology. So in the first one, we've given a sequence 5, 7, 9, 11, 13, 15, comma, dot, dot, dot. So write down the next 3 terms in that sequence. Well, hopefully you can see that they are going up by 2. And so the next 3 terms would simply be 17, 19, and 21. Write down term 4. Well, term 4, that's what the T4 represents. It's the 4th term along there. So 5, 7, 9, 11 is our 4th term. Finding a formula. Now, this is just going to be by inspection, but later you're going to learn a technique for this for 2 different types of sequences. But just for here, let's see if you can find one. You might want to pause it and give it a go. The nth term of the sequence, Tn, here is given by 2n, because it's going up by 2. But 2 times 1 is 2. I want 5, so 5 plus 3, that's going to give me 5. And when n is 2, 2 2s are 4, plus 3 does give me 7. 2 times 3 is 6, plus 3 does give me 9. So I can see that that formula is working for the values in that sequence. I can use that formula now to find the 50th term. So if Tn is equal to 2n plus 3, then term 50 is going to equal 2 times the 50 plus 3, which is equal to 103. Example 2, given the sequence 1, 4, 9, 16, 25, comma, dot, 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 write down terms 6 and 7. So the next term will be the 6th term. So term 6, hopefully you can see the pattern. It's going to be 6 squared, so 36. And term 7 is going to be 7 squared, so 49. That's just by looking at what we think that pattern might be. So you can see there that Tn is equal to n squared. It's the square of that n value. And so term 35 is simply going to be 35 squared, which if you use your calculator comes out to be 1,225. The nth term, example 3, of a sequence, what's the possible values of n? So Tn is the nth term of a sequence. What's n? Well, we can find the first term, we can find the second term, the 10th term, the 100th term. The term numbers have to be whole integers. So we can't find term 1.5. We can't find term pi. We need it to be term 1, term 2, term 3. Can't even find term 0, and it can't be negative. So in other words, what we're saying is that n has to be whole numbers starting at 1. Term 1, 2, 3, 4, etc. A way to say this would be that n belongs to this set of positive integers That's a notation, that's z plus for the positive integers, and that's an n belongs to symbol there. Example 4. A sequence is defined by Tn equals 261 minus 3n. Write down the first term. Okay, so we have a formula, so we can put the 1 in. And so it's going to be 261 minus 3 times 1. So that comes out to be 258. So there's our first term. Our sixth term, term 6, is going to be 261 minus 3 times 6. And so if you use that on your calculator, you get 243. So that's our sixth term. Which term in this sequence is equal to 90? Okay, well, in that case, what we're saying is that the nth term, which is 261 minus 3n, has to equal 90. And so we're solving this now. So 3n is going to equal 261 minus 90, which is, use your calculator there, 171. So we have 3n is equal to 171. So n comes out to be 57. So it is the 57th term. You'd have to go along to the 57th number in that sequence to hit the point where the term is equal to 90. Now, to determine whether or not 158 is a term in the sequence or not, what we do is we get the formula for the nth term. So the formula for the nth term, I might rewrite it here, it was equal to 261 minus 3n. What we're going to do is we're going to put that 261 minus 3n equal to 158 and see what term number it comes out to be, solving it the same way as we did in the last question. So for this one, we get 3n, bringing that over as equal to 103 when you subtract. And so when you divide by 3, we get, this comes out to be 34.3 repeater. Now you can't have the 34.3 repeater term. And so that tells me that 158 is not a term in that particular sequence. How many terms are positive? Okay, so to work out how many terms are positive, we need to have Tn greater than 0. Now Tn is 261 minus 3n. So we need that expression there to be greater than 0. And so bringing the 3n to the other side, we have 3n is less than 261. And so n comes out to be less than 87. So there are going to be less than 87 terms which are positive. And so therefore, there's going to be 86 positive terms. Okay, example 5. A sequence is defined by Tn equals 2 times 3 to the power of n. Write down the first term. Okay, so term 1 is equal to 2 times 3 to the power of 1. We simply put that subscript 1 where the n is. All right, so this one comes out to be 6. Term 4 would be equal to 2 times 3 to the power of 4. Putting the 4 where that value is. And if you use your calculator there, you should get 162. Part C, which term is equal to 4,374? Okay, well, same idea as before. So essentially we're saying the nth term, whatever it is equal to 4374. So that means that 2 times 3 to the n is going to be equal to 4374. And so we've simply got to solve this now. So dividing both sides by 2, we get 3 to the n is equal to 2187. Now, I'm going to use logarithms here to solve this. Don't want to use trial and error. So taking the log of both sides, I've got the log of 3 to the n is equal to the log of 2187. I'm going to use a log law now to bring the power down the front, and so that becomes n log 3 is equal to the log of 2187. And so dividing both sides by log 3, I get n is equal to log 2187 divided by log 3. And when you put that in the calculator, and you can use either log base 10, which is just your log button, or ln, your natural logarithm button. Either one will work. I'm just going to use the log button, and so I get n equals 7. How many terms of this particular sequence are less than 1,000,000? So we're saying here we need the nth term to be less than 1,000,000. Lots of zeros, so 2 lots of 3 to the n is going to be less than 1,000,000. Dividing both sides by 2, I get 3 to the n is less than 500,000. And so taking log of both sides now, I get log of 3 to the n is less than log of 500,000. Now the inequality stays the same at this point. The log function, if you draw the log function, it looks like this when you draw it. The log function is an increasing function, crosses at 1. It's an increasing function, and so the greater the value of the number, then the greater the log of it. And so when you take the log of both sides of an equation, the inequality sign stays the same. All right, now I'm going to bring the power down the front using the log law, and so we get n log 3 is less than log of 500,000 divided by, there we go, next one is going to be n is, now I'm dividing by log 3. So when you divide by log 3, you've got to be careful as to whether you're dividing by a positive or a negative. Now on the graph I've just drawn, you'll notice that the log of 1 is 0. If you take the log of a number less than 1, so between 0 and 1, it's negative. And in that case, you would be changing the sign when you divide. But log of 3 is positive, and so I'm dividing by a positive, and so the sign will remain the same. So I get now log of 500,000 divided by log of 3, and so n comes out to be less than, when you calculate that, 11.94 and so on. And so we're going to say therefore that how many terms are less than, it will be 11 terms. Needs to be less than 11.94. So there's 11 terms. Okay, going to question number 6. A sequence is defined by Tn is equal to -1 to the power of n times n outside of n minus 1. Write down the first 8 terms. So this is just to get a bit of an idea of what this sequence looks like. Write down the first 8 terms. Okay, so term 1 is going to equal -1 to the power of 1 times 1 times 0. Well, anything times 0 is 0. So this term 1, is 0. Term 2 is going to be -1 squared times 2, because n is 2, n minus 1 is 1. And so -1 squared becomes positive now, and so it's positive 2. Term 3 is equal to -1 to the power of 3 times 3 times 2, because it's times n minus 1. Okay, -1 now becomes negative, so it's negative 3 2s is 6. Term 4, it's going to be -1 to the power of 4 times 4 times 3, n times n minus 1. And so -1 to the 4 now becomes positive, 4 3s are 12. I'm going to go up and over here just to save room. Term 5 is going to be equal to -1 to the 5 times 4. And so that becomes, now it's negative, so -20. Term 6 is equal to -1 to the power of 6 times 5. Just putting the values into the formula, you can see the pattern that's occurring. This one's now positive again, 6 5s are 30. Term 7 is equal to -1 to the power of 7 times 7 times 6. 6 7s are 42. So this is negative now, -1 to 7, -42. And finally, term 8 is equal to -1 to the 8 times 8 times 7. So this now is positive again. You'll notice -1 to the power of 8. So what effect does the -1 to the n have on this sequence? Well, you'll notice that -1 to the 1 is negative, -1 squared is positive, -1 cubed is negative, -1 to the 4 is positive. So what it does is it makes the sign of the sequence alternate between positive and negative. So it makes the sign of the sequence alternate, positive and negative. Okay, question 7. If Tn is equal to 4n minus 7, find the value of d such that Tn is equal to Tn minus 1 plus d. Okay, so what I'm going to do is just get a picture of what this pattern is equal to. So if Tn is equal to 4n minus 7, what would term 1 equal? Term 1 is going to be 4 times 1 minus 7, so that comes out to be minus 3. What would term 2 be? It would be 4 2s are 8 minus 7, so that's 1. Term 3 comes out to be 12 minus 7, so that's 5. So can you see here, just by inspection, that if I wanted the next term, I can see the pattern is it's going up by 4 each time. So the next term would be the previous term plus 4. We are adding 4 from minus 3 to 1. You add 4 from 1 to 5. We add 4. So I can see that in this particular sequence, Tn is equal to Tn minus 1 plus 4. And so therefore the d value here, which by the way stands for common difference, the d value here is 4. We're going to learn more about this a little bit later in a future lesson. Part B, write down the first 8 terms of this particular sequence. Now you'll notice that this formula is not an explicit formula. This is called an implicit formula. We need to know the previous term to find the next one, because Tn is equal to double Tn minus 1, so double the term before it, minus 1. And it only works for Tn where n is greater than or equal to 2. Term 1, we're told, is 3. So the first term's 3. But beyond that, we can use the formula. So term 2 is going to be equal to 2 times term 1 minus 1. Okay, so that's going to be 2 times the 3 minus 1. So 2 3s are 6 minus 1 is 5. So term 2 is 5. Term 3 is equal to 2 times term 2 minus 1, because you're putting in 2 times the term before it. Tn minus 1 is the term before it. So that's 2 times, now term 2 we found was 5 minus 1. So that's going to be 9. So term 3 is 9. So speeding that up now, term 4 is going to be 2 times the term before it, which is 9 minus 1. So that's 17. Might come over to this side again for room. Term 5 is going to be 2 times the term before it, so 2 times 17 minus the 1. I think we get 33. Term 6 is equal to 2 times the 33 minus 1, which is 65. Term 7 is 2 times the 65 minus 1, which is 129. And the last one of us is to find is term 8. So it's going to be 2 times the term before it, minus 1. And that comes out to be 257. All right, so that concludes the lesson on the notation and terminology in sequences. You can now go on and complete that first exercise.